Hello Matthews, Gatos here. In this video, we're going to look at the mean value theorem. So let's get started. Before we can talk about the mean value theorem, we need to review continuous and differentiable functions. So a function is considered continuous on some sort of a closed interval, a and b, if it takes on every value between the endpoints f of a and f of b. So that means a function, there can't be any breaks in the graph, it can't jump over any values between f of a and f of b. If a function is differentiable on an open interval, because we can't have derivatives at the endpoints, then it is continuous and the left-handed limit is equal to the right-handed limit. Now remember, if a function is continuous, it doesn't necessarily mean it's differentiable. However, if a function is differentiable in the question, if it states that, it automatically implies continuity. So what the mean value theorem says is if we have a continuous function on a closed interval and a differentiable function on an open interval, then we know there exists at least one number c in that open interval such that f prime of c is f of b minus f of a all over b minus a. What does that mean? So what that means is at x equal to c, that is an instantaneous rate of change. That's like the slope of a tangent line. And it will equal somewhere in that interval the average rate of change, which is the slope of the secant line. So let's look at what that would look like maybe graphically. So let's say I've got, I don't know, some sort of a polynomial function like that, okay? And I have some point A on the graph, so we'll say A is right there. So let's line that up and the corresponding f of A. And then we've got some point B on the graph, we'll say there. And then the corresponding f of B. Okay, if I'm going to connect those two dots, that forms a secant. So the slope of this secant line between A and B, the mean value theorem guarantees there is some point C in this interval, let's say there, and corresponding f of C. So there's some point C in this interval such that the slopes are going to be equal. So this is the slope of the tangent line, and this is the slope of the secant line. So there's some point C in that interval where the instantaneous rate of change will be equal to the average rate of change. So when we do this, just like the intermediate value theorem, that end statement is really important. You cannot use the mean value theorem unless you state continuity, you state differentiability, and then you can find your value of C in this interval. So let's try our first example. So in this example, I want to determine, can the mean value theorem be applied to the function on this closed interval? So we've got f of x is equal to the absolute value of 2x minus 1 on this interval. So 2x minus 1, I know that that is an absolute value function. So statement number 1, f of x is an absolute value function. And we know that absolute value functions are continuous everywhere. So f of x is an absolute value function, therefore continuous everywhere. Okay, requirement number 1 met. Requirement number 2, is f of x continuous? Well, I know that absolute values are continuous everywhere except for where the piecewise functions join. So if I look at this graph of absolute value of 2x minus 1, doing a very rough sketch, okay, I know that the absolute value looks something like this at the point 1/2. So I know that f of x is continuous, yes. It's also differentiable everywhere else but this point right here. So I need to check in this closed interval here, does it include the point 1/2? It does include the point 1/2. 1/2 is in between -2 and 3. So x equals to 1/2 is not differentiable at that point because it is a corner. So therefore, and I'm going to say actually it's not differentiable and it's on that interval in between -2 and 3. Therefore, mean value theorem does not apply. So we cannot use the mean value theorem for this question. Okay, let's try another one. Okay, in this scenario here, we have Giorgio running the Disney Marathon in 2 hours and 20 minutes. If a marathon is approximately 42 kilometers, show that at least twice throughout his race, he was running 18 kilometers an hour. So let's go through our requirements. Okay, so we're looking at running. So speed is continuous. And I also know if I were to graph distance versus time, the speed graph, it would also be differentiable. Speed is also differentiable. Okay, so my first two requirements are met. Okay, so let's look at the average rate of change. The average rate of change. So we have his distance, 42 kilometers, divided by his speed. We want to do this in hours, so this is 2 hours. Let me do this on the side here. 2 hours and 20 minutes out of 60 minutes in an hour. That would reduce to 2 1/3. So 2 1/3 hours. So my average rate of change is 42 kilometers in 2 1/3 hours. Okay, that is going to simplify to be 18 kilometers an hour. That's my average rate of change. Okay, so since I'm continuous, since my speed is differentiable, I know that the MVT applies, mean value theorem applies, and therefore there is at least one value. We know there's at least one value of C such that the derivative of f of c is equal to the average rate of change, which is 18 kilometers an hour. Okay, now we're looking at when he is going to be running the race at, oh, this is a little typo in your question. It says 17. My apologies. Let's just change that. So we'll change that to 17 kilometers an hour. I apologize. So the average rate of change is 18 kilometers an hour. So that means to get to 17 kilometers an hour, he is going to reach that time when he's speeding up and then again when he is slowing down. So we know at least twice his instantaneous speed is going to be 17 kilometers an hour. So speed will reach 17 kilometers an hour at least twice, 2 times, speeding up and slowing down. In that interval. And that would be between 0 and 2 1/3 hours, not including either. Okay, let's look at another question. Okay, so I want to determine if the mean value theorem can be applied to this function on the closed interval, and if it can be, find all values of c that satisfy the theorem. Okay, so f of x, this is a polynomial, and we know that f of x, since it is a polynomial, it is therefore continuous everywhere and also differentiable. No breaks in the graph, no asymptotes, no piecewise functions. So f of x is a polynomial, so continuous and differentiable everywhere. So definitely on that interval as well. Okay, so we know that the mean value theorem applies because it meets those two conditions. So I know that there is at least one value of c on this interval, and we're going to use this as a and b such that f of b minus f of a all over b minus a. Okay, so looking at this, we have f prime of c is equal to, so now we want to come up with the intervals. So let me just move this over here. Oops, a daisy. There we go. Okay, let's move that over. So first of all, I have my polynomial graph just so you can see it. It's a cubic function, continuous, differentiable everywhere. Okay, so I want to come up with something. I want to look at each of the values here at the endpoints. Okay, so here's my endpoints here. Let me just draw on this graph here. So this is the point at x equal to -1. This is the point at x equal to +1. Okay, now I know I can plug it into the original equation, or I could use my graphing calculator if this was allowed to find out the corresponding points that go with it. So when x is -1, my y value is at 0. So I have -1 and 0 as a point on the graph. And then when my x value is 1, it has a y value of -2. Okay, so let's apply this to our formula. So f of b, so that's going to be f of 1, take away f of a, all over b minus a. So that means f prime of c is equal to, so plugging this all in, I'm going to have f of 1, which is -2, minus f of -1, which is 0, all over 1, take away -1 is 2. So simplifying this further, I'm going to get a slope of -2/2, which is -1. So what this means is if I were to connect those points, okay, I'm going to have here a slope which is -1. Okay, so this slope right here of the secant, that's what f prime of c is. Okay, so this is the slope of the secant line. So what I know is there's going to be a point in there that I have a tangent line. So there's my secant line. I know that the mean value theorem guarantees at least one value of c in this interval where the slope of the tangent line is going to equal to the slope of the secant line. So what I have to do is just a little bit more work. I know that the derivative f prime of c is equal to -1, and I have my function. So let's set that. We're going to find the derivative, and we're going to then set that equal to -1. So if f of x is equal to x cubed minus x squared minus 2x. Let's use power law for the derivative. 3x squared minus 2x minus 2. Now I already know that that derivative, the slope, is going to be -1. So I'm just going to solve for my value of x. So add 1 to both sides. And then I'm just going to factor this. So 3x plus 1 and x minus 1, set each factor equal to 0. So one value of x is -1/3. The other value of x is 1. Okay, but I want to go back up to my closed interval, which was between -1 and 1. So between -1 and 1, it does not include 1 because I have to do this when I look at the derivative. I'm looking at it on the open interval. So the only one that applies is x equal to -1/3. And you can see on my calculator, I actually drew the slope of the tangent line right there at that point, which is -1/3. And you can see that the slopes are in fact equal. So the value of x that guarantees that, or the value of c, is -1/3. So I hope this helps explain the mean value theorem. And what an interesting name for that. A mean value theorem. Mean, I don't know, do you think that that's an appropriate name for this? Value, it does have value to me. I hope it has value to you as well. So I hope this video helped. If it did, give it a thumbs up and hit subscribe so that I can help more mathies just like you. Thank you for watching, and I'll see you for the next one.